This is going to be the lecture on wave properties. I was just actually showing off and meant to have this up. We have a wave demo up on the website right now, up on Google Classroom that you can look at just very quickly. You got manual, which you can put this up and down, pulse, which you can click and it'll put a single one out, oscillate, which will keep going, and you can change a variety of things at the very bottom. Notice one thing that instead of, in this particular case, look right here, look at where we're at, okay? So if I put on oscillation, you'll see frequency right here. If I change that oscillation back to pulse, you'll notice it changes it to pulse width. And what is the units of that pulse width? It is in seconds how much time it takes to give one particular cycle in that particular pulse. All right. So as I talk about stuff today, this is going to be used quite a bit. You will also notice that there's settings over there on the right side that I haven't discussed yet, and that is for good reason. Okay. The first thing that we need to talk about in wave properties today is what is known as reflection. Okay. So let's put this up here. Reflection. Reflection is a property of waves that does not, it sort of doesn't have to do with matter. Okay. By the way, kind of the opposite of a wave is thinking about just like a part of point mass. Okay. So if you want, anytime I'm thinking about a wave today, you're talking about energy going into a barrier, which I'll talk about in more second. Okay. The counterpart of that is just taking a tennis ball and throwing it against the wall. So to a certain degree, we do somewhat expect reflection out of point masses as well. If I throw a tennis ball against the wall, you expect it to bounce back. But not every object bounces back in quite that particular way. Every wave is going to deal with reflection. The first type of reflection you're going to see, I'm just going to kind of draw a string here, is one that is moving into a fixed boundary. In which case, what you're going to see is a demonstration of Newton's third law. What is Newton's third law? For every force, there is an equal and opposite force. So, a boundary is anytime a wave hits another material or goes into another material. So simply today, with this spring, the boundaries are, pretty obvious, where this thing is attached. And looking at this guy real quick, is it fair to say that you can see that this is indefinitely fixed? Yeah, it's held in place, okay? And because it is held in place, we are going to be dealing with Newton's third law. Because, watch this. What is happening when I put a pulse in, I put my hand up, and I put a wave in. And that is energy that is going into the system. As we've said before, as that energy comes by and hits me in the hand, what does it force my hand to do? The exact same motion that I put into it to begin with, right? That wave comes by and forces my hand up and down. So if it comes into here and tries to go up and down into this is fixed. So what is this going to do? Put an equal and opposite force. So if this is putting a force up, what is this putting a force on it going? Down. So what that forces it to do is it causes the wave to reflect and invert. And you can, of course, see this by putting a fixed boundary. I'm just going to go ahead and put a pulse here. Just notice very quickly over here on the other side. Put a pulse in and ta-da, it flips over on the other side. Let's actually go a little bit less dampening because it's kind of going. And you can see it reflect. As a matter of fact, it reflects on both sides because it's fair to say that both of these are relatively fixed. Does that make sense-ish? Okay? Now, what's the counterpart of that? The counterpart of that is extraordinarily difficult for me to show. Also, another example, I said boundaries. So a fixed boundary could also be, here we are, a stringed instrument. Okay? A stringed instrument, based on its creation, is going to have fixed boundaries on both sides. Like even if I do an open string, you'll notice fixed right over here. The string comes up and is held in place by, I don't remember what that's called, that particular bar. Okay, and then it's held in place over here. So fixed, in place, they're not moving. So that means they're both fixed on both sides. Now, The other situation you can have is what is considered, let's go over here, a free boundary. Now, for demonstration purposes, what you usually see is this is a string with some like loose end that is allowed to just freely move up and down. And because it is allowed to freely move up and down, or it is a free boundary, we do not have the same type of Newton's third law situation because it's not actually putting a force on this. So what it sort of is like is it's kind of like, okay, so like imagine I've got this and I just had more string. I think this would be obvious. What would you expect this string over here, once it gets to this location, the string should just continue on, yes? Now, the reason why this occurs is because this is putting an upward force on this next part of the string, right? Where it puts the most force on it kind of right here to change it the quickest and a little bit and then down and that type of thing, like down over here, and that causes the string to kind of do the exact same thing all the way through. When you get to a free boundary, it still sort of does that, but back on the previous string. So what happens with a free boundary is it will reflect but no inversion. So we can see this over here by going a loose end, and this is kind of the demonstration that we're looking at right here. Now, notice that this side is still going to be fixed, so you can certainly have both one on either side, and notice what happens when it hits the free boundary. It just reflects back the opposite way, but does not invert on the opposite side. Does that make sense? Okay. I wish I could give you a bunch more demonstrations here, because quite frankly, I feel like to ask, does it make sense? You go, well, yeah, I guess you just showed it to me and I've never really seen it before. It kind of benefits having experience to kind of give you the idea of this stuff making a little bit more sense. So that is reflection in a nutshell. Now, reflection, as I've mentioned already, has a huge part to do with instruments. So here we have two fixed ends. Okay. Here with the kalimba, this is a kalimba right here. What you will notice is that there is a fixed end on one side, but this side right over here is allowed to be completely free. It's allowed to go up and down. So we have fixed on one side and free over here on the other. Does that make sense? Okay? Or is there a question?
Yeah, it's a question. But when you play like a stringed instrument, so like when you play it, when you hit it, like the sound comes from like the energy of the lead, like it's in the string.
The sound comes from, so I put energy into the string itself, yep, vibrating the string up and down. But then that string hits air at a very, very specific frequency, right? And that's what sound is. That's that movement of air in my ear in this particular case. Now, next, this is just a piece of metal. It's not necessarily an instrument, but all of you know for a fact that if I drop this on the ground, it'll make a particular noise. Now, in this particular case, would you say the boundaries are free or fixed? Free. Both of them are completely free, allowed to move. Now, in this particular case, I have another piece of metal. Now, part of it does depend on what type of metal, but for the most part, metals are pretty fast, so their velocity is pretty high. So right here, I also have two free boundaries. But the fact that it is smaller means the wavelength of distance must automatically be small. Yes? And given our conversation on Friday, what does that mean will automatically happen to the frequency? The wavelength goes down, frequency goes up, and as I drop this on the ground, what should we expect? It should be, is it in fact higher? Simply put, only difference in those two particular guys is the length. You can get a similar effect with pipes. As a matter of fact, organs are your best bet on this particular guy right here. Okay, here I have two free boundaries. Now, what's weird to think about? Now, as I do this and I'm making these particular weird noises, please understand that there is kind of it's not fair to talk about the pipe because who's really changing the pitch? I am by changing my armature at the speed with which I vibrate my diaphragm up and down. So probably a better way to do this would be. Just make it in your hand. Do you hear a difference?
Yeah.
What's the difference?
The left one's higher.
Oh, a lot higher. This one's definitely, this one right over here is lower. A little lower. Do you not hear that this is a higher pitch?
Yeah, I'm done.
It's not tone. It's not tone at all. Like anybody could be able to do this. Get a lower pitch, higher pitch. No, is that not helping? Okay, there it is.
Use it like a woodpecker, like
Yeah.
Just think it got higher.
Yeah.
I can hear it now that you said it.
So fire.
Okay. I mean, we're talking the simply the physics, the very simple physics of sound. I wish I could get a lot more into it from there. But essentially, we are dealing with the main difference between all of these is simply one restoring force. Metal is going to have. Would you guess metal would be faster or slower waves traveling through it? Much faster, yes. And why would that be?
The metal's gonna die.
No, not why. That is true, but that's not why. It's a good guess. What? Do you remember what we said? The main purpose, how sound travels. I've got air molecules. I have these air molecules evenly spaced out, and this guy moves kind of at random at a relative speed. Yes. Okay. And then randomly, it has to come over here and hit this guy, and then that's got to randomly hit this guy, and that's going to eventually runs over and hits your ear. Now, all of that happens obviously pretty quick, which is why sound in general is traveling at about 343 meters per second, or Mach 1 if you prefer. Anyway, so why would metal then be faster? Closer together. So what's going to happen to that random effect? It's going to happen much quicker in that particular case. So yeah, metals travel about 3 times as much as air. So where's liquids in that? In the middle, correct. Yeah, sound travels much faster in a liquid than it does in air because they're simply tighter together, and metals, solids are going to be the fastest. Yes.
So why does the length of the metal make the wavelength shorter and longer?
Well, again, I wish I had more time. And let me get a little bit further into today's lesson, and I can probably do a little bit of that. Okay, yes.
So it just depends on the density.
In terms of the speed, yes.
Okay.
Absolutely, yeah. And really, it comes down to, like I said, restoring force. Like, what force is it that's forcing this to like travel through? In this particular case, the spring, right? I can tighten up the string. Okay. And it should travel much faster through that particular medium than it would if it was less tight. Still pretty quick, but not as. All right. So, like I said, you can mess around with this. You can see this type of thing throughout. But the main thing is, in a fixed boundary, if it moves into a fixed boundary, then it is going to reflect and invert. And if it's going to go into a free boundary, it's not going to invert. Now, this is moving between mediums. Boundaries are pretty easy. But if I had, say, this solid string, okay, and then about, I don't know, 3/4 of the way down, I decided to tie just a simple piece of string instead, okay? As the spring went into the lighter string, what boundary would that be like? Free or fixed? Free, because it's allowed to move much easier in that particular case. Vice versa, if I put energy into the string and went into the metal doesn't move nearly as much, and therefore would act like a fixed boundary. So this should be pretty obvious. I think in a certain way, if I talk, air is going to hit this wall. Yes? Like even if I don't aim at you guys whatsoever, and I just talk directly into this wall over here, all of you expect to still hear me because sound is hitting the wall and bouncing back and forth. Wall is fixed or free? What's that? Fixed. Yeah. It's a solid surface. It's not moving very much. What's a little bit strange to think about, although you do know this, is that hitting an open air like that right there, if I just aim my sound directly at that, it also creates a reflection back in. This is a little bit stranger because wait a minute, man, there's nothing in the way. So what causes this to happen? The gap creating right here, okay, causes these. Now here's probably the easiest way to think about it. Okay, if I start talking right here, I create this wave outward, molecules moving like this. Yes, molecules moving like this. So I've got a whole bunch of molecules right here that are doing this. They push all the way out, and they come all the way back in, and they go all the way out. Now, is that going to create a wave out into the hall? Yes, in all sorts of different directions. You can kind of think about it like water, right? Like if I splash water right here, it's going to make a ripple outwards, yes? What's that going to force the water in the door to do? Bounce up and down. And that bouncing up and down right here kind of creates its own ripple outwards into the hall, but also back into the room itself that is also being reflected. All right, next. Let's talk interference. Reflection is what happens when a wave hits a boundary. Interference is what happens when a wave hits another wave. The first thing to understand about two waves traveling at each other is what is actually moving. We've already discussed this. Is there a thing that is moving? This is one of the primary differences between waves and point masses. If I have two tennis balls traveling towards each other and they hit each other, very simply, what's going to happen? They're going to bounce back. Of course, they're going to contact because they're physical stuff, and there's going to be force between them. It's going to push the opposite way. Second law, blah, blah, blah. What is a wave? Energy. It is not an actual thing. So what's going to happen to these guys as they pass through each other? They simply pass through each other. Entirely going through each other, having absolutely no effect on the other one. And of course, you ever want to see this or demonstrate this, you can of course look at this guy. Watch what happens when they meet. Restart here. Let's give it a little bit more time. Oops. Do they affect each other? No. They just continue on through us. So let's get rid of dampening for a second so you can just keep seeing this. Interference is what you're looking at, simply put, when they actually are in the exact same location. And I think just visually from this right here, you can pretty much see what happens if they are going, excuse me, if they are on the same side in the middle. They do something called constructive interference. Simply put, they add. If they're on the same side, like right there, you'll notice that the amplitude in that particular location gets twice as big. Now, what happens if they are on, there it is, there's constructive interference, that's not. This next one's gonna be constructive, there it is. So what happens when they hit each other and they're on opposite sides of it? They subtract. That's got its own name as well. Oh, look at you. Now, there is a small difference that I need to be careful with vocab and destructive, and it has to do with this. If my amplitude of one is not the same as the other, okay? If, say, this is 2A and this is 1A, in amplitude. When they meet, of course, you would expect just 1A above right here. This is known as destructive interference. If you have them the exact same amplitude, you get just kind of a small difference to it, complete destructive interference. And what is the sound of complete destructive interference? Silence. Literally, it is silence. So let's talk about a couple ideas in actual practice of constructive interference and destructive interference. Let's start with constructive. And I'm going to put out a wave that is just a tuning fork. A tuning fork is just this. Simple sinusoidal wave bouncing up and down coming at you. Okay? If I were to play a wave that was the exact same frequency, that would mean it would have the exact same wavelength at the exact same location. Of course, these would just simply double. Oops, that was dumb. Can anybody see how I drew that wrong? I drew the amplitude bigger, but I also changed the frequency. The wavelength does have to stay exactly the same in both of these. Now, how would this be different in terms of sound?
The one with more frequency would be higher pitch?
No, not higher pitch. Because it's the exact same frequency, so it's the exact same pitch. Louder. Simply louder. If you've ever been in a room, specifically like where students are allowed to freely work on whatever they want, okay, or even let's talk about like if you've ever been in like the intermission of like a play or a concert or something like that, you're sitting there. What you'll find is at the very beginning you start talking to everyone else in the room, and a normal tone of voice, normal volume. You want them to hear you. You're not gonna walk up to a random person that you care about and just start screaming into their face. Okay, you're gonna talk to them normally. But then everybody else is going to start to bring up particular conversations. What you're going to find, especially if you were not in the room and not particularly paying attention to it, you kind of walk in to an intermission. Holy crap, it's loud in here. How is it so loud in here? If you were to go to any particular individual conversation, what you would find is they are attempting as best as possible to talk in a normal tone of voice. What's happening in this is that you have this conversation over here and this conversation over here, and in particular areas where they are both on the same side, what's happening to that amplitude? It's getting bigger. It's getting much bigger. So despite the fact that I'm talking in a normal tone of voice and you're talking in a normal tone of voice and everybody's talking in a normal tone of voice, if someone were to walk in, it's ridiculously loud because we do not hear individual conversations. We hear all of the conversations at the exact same time. Now, that being said, the opposite side of the coin is you go, yeah, great, Spainhour, it's loud in there. But I still can't understand what the heck the person next to me is now saying, despite the fact they're talking to me just like they normally talk to me. And the reason why is, while constructive interference is happening for sure, what is also happening at the exact same time? Destructive interference. So if I start having a lecture in here and I'm trying to talk about blah, 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 whatever, who cares, it's Spainhour, we don't need to worry about that. And someone next to you is kind of either rudely or just trying to honestly have a quick conversation with someone that matters, who cares? What's happening in your ears, you are hearing Spainhour talk. You are hearing that person talk, and you do not get either. Your brain is incapable of deciphering one versus the other. It's not like you could even look at a person and concentrate super hard because the air molecules are bouncing back and forth. There's just a certain set of air molecules. You do not get one and the other. You get both, the combination of both of them. So, watch this. If Spainhour were to say talk like, how do I lose this like every time? I just have. Okay, if Spainhour were to talk like this and have this conversation right here, now the actual like vibrations of this get a little bit strange, and this is just I'm talking higher pitch, lower pitch. Well, we could talk about that if you go into. I don't have time, sadly, but and you say somehow we're able to match him so that you did this. I don't think you could. But if you could, what would the person hear? Literally nothing. It is entirely possible for you to play. As a matter of fact, anybody have noise-canceling headphones? Noise-canceling headphones are not just muffling the sound. What's happening with the noise-canceling headphones is the headphone is right here. You ever notice that on a noise-canceling headphones, they have speakers on the outside? Like they have this little thing on the outside, not the inside, okay? What it's doing is it is attempting to take this yellow outside noise. Now, they're really good, but the technology is nowhere close to what I just drew, okay? What the truth of the matter is, actually, let's go back real quick. So before Spainhour drew that second one, Come on, go back. Going. Yes, I was drawing pink. It's fine. I knew what I was doing. Okay. Here's what noise canceling headphones do. Now, is that going to entirely cancel out all the sound?
No.
Is that going to cancel most of the sound?
Yeah.
Yes. And that's exactly what it is. Now, that is, of course, in combination with also muffling stuff on top of it to decrease the sound from the outside. So whatever is in fact. So this means, and you would never actually notice this, noise canceling headphones are playing a noise. They are playing a noise into your ear. But they are playing the exact opposite noise of what is coming into your ear. So the direct result is not any sound whatsoever, despite the fact they are playing a sound. It is just the opposite of what's going in. And so they try to make silence. Yes.
So that's why the destructive ones are silent, because they're always like opposite and they just cancel each other out to equilibrium.
Yeah, think about it. What is sound when I draw it up here? Sound is molecules going back and forth like this, right? So if I play the opposite sound as molecules are being pushed this way, I'm pushing them that way. And so this is the sound that's being played. This is a tuning fork. This is what I'm playing over here. This is the force that I'm putting onto it. So what is the actual result on that air molecule? It sits there. And what is the sound if that air molecule is just sitting there? Silence. Yes.
What does like the top and bottom
Excellent
part
question.
represent?
Excellent question. In terms of sound, now in terms of waves, obviously it's easy to see, it's just up and down. In terms of sound, you were talking about high pressure areas and low pressure areas. As a matter of fact, I have an exact setup for that. Thank you for leading me into that. Look at you. Jaden and I talked about this ahead of time, actually. So
No, we didn't.
we did. We totally.
I just asked awesome questions.
Is that what it is? All right, fair enough.
Speaking of awesome questions, I heard that second place got nerdy T-shirts for the boat ride.
I think that is correct. Yes.
My little sister is really excited.
Good. I hope that you guys get Barbie. I think that would be appropriate. But you do whatever you want. We'll talk after. So here's a very slow depiction of sound, essentially. Okay. What you're noticing is the diaphragm vibrating back and forth, and it's really interesting because it really looks like something's moving up here, right? Like you can see them moving to the right. But if you were to track any one particular molecule, like for example the fact that we've highlighted red, we've highlighted I think 3 different red molecules up there, and watch what they're doing. Are they actually going anywhere? No. So to answer your question, okay, silence is actually air molecules evenly spaced out. The high part of the wave are what we consider the high pressure right here. These guys right here, those high pressure parts. And then actually we get the opposite when it goes the opposite way. So like if you have a tuning fork, as the arms come inward, they create a compression. That's the high part of that. That's that high pressure system. Okay. And as they move apart, they actually separate the air, making the pressure less than normal. That's what's known as a rarefaction. Not important, but you see these spots, the easy spots to see are the high pressure. But if you kind of look in between, you'll see like a lack of air molecules in there, right? So the high parts of the wave that I drew on the top up here, that would be a high compression. And this guy right down, actually let's change colors back so I'm not going more. That would be a compression, and that would be a rarefaction, which makes sense then, considering what we just said, because if I just let yellow play, that's Spainhour's normal speaking voice, but if you want to put the headphones in so you don't have to hear him, then they're going to play this. When a compression comes in, they're going to play a rarefaction. Compression means there's too many molecules. Rarefaction means we're missing molecules. Those both played together is evening it out. There's the same number of pressure of molecules. And vice versa up here. This is Spainhour playing a rarefaction on the bottom right down here, so the speakers play a compression to counteract that particular part. Does that make sense-ish? Yes.
I just had another question. I was just kind of making sure that I understood this right.
Uh-huh.
But basically, so like frequency is equal to like what your pitch is, and then amplitude is like how loud it is, and wavelength is the speed.
Wavelength is not the speed. Wavelength is probably the hardest for you to understand because it is the one that you don't necessarily have a direct connection to. Wavelength is easier for us when talking about stuff to visualize. Like if I draw a picture on the board, I'm not easily going to be able to draw for you a frequency, right? Because that kind of requires an animation. But simply put, based on the equation that we did yesterday, V equals wavelength times frequency, you can kind of see visually from a wavelength what's happening to frequency. Meaning if I draw this wave and I draw that wave, what did I just do to the wavelength? I made it small. So what did I do to the frequency? Made it bigger. So, and I can show you that because I'll draw them the same size now. The frequency of this completed once in its distance. This guy right down here completed 1, 2, 3, 4 times. Meaning this bottom one has 4 times the frequency of this one up here because its wavelength is 1/4 the size.
So when you affect your wavelength,
You in turn affect frequency. This is
affect
what we were trying to talk about. Yeah, and this is what I was trying to talk about on Friday when I said this. Listen, each one of these strings on here is of a different size, so I'm not going to like try to mix and match right here, but let's just focus on a single string. I'll focus on this, where's the heavy one? Weirdly, it's this guy right here. And I'll press right here. What am I doing when I press in here? Creating a boundary. And yes, in turn shortening the wavelength. And now, what did I just do to the wavelength? I made the wavelength smaller, which in turn made the frequency higher. Yep. Yes.
Why is it? You affect the wavelength is
You are still.
string.
What's that?
Is the whole string moving, or is it?
So yeah, absolutely.
Is one.
Absolutely. So like when I do this, if I don't touch anything, my boundary is from here to here. Okay. If we really got, man, I wish like I'm looking at the time and I need to hit one other thing before we're done here today because the questions you're asking are incredible and are planned for like just if I just gave it like a day or 2 more, I would 100% do it, and I would totally continue if not for the fact that I know you'd probably appreciate relativity even more. Yeah.
So is the velocity always the same?
Remember we said that the other day that velocity is controlled by the medium and the restoring force. Okay, so I can change the velocity in this string. Now, have I changed the wavelength at all? Nope, it's the exact same size. Okay, it was in tune. It's not going to be in tune anymore. I don't have that. I don't have the ear for putting it right back immediately. But so the wavelength hasn't changed, but the velocity, because I'm making the tension less, velocity is getting less. So since the wavelength stays the same, velocity gets less, frequency also gets less. Now, changing this in the middle of a song would take a ridiculous ability that I think that very few people, maybe some masters, could actually use. And I think some masters actually do use it where it makes a particular interesting sound when by changing the velocity and throughout, you can obviously do that the same as playing. So some very high level like guitarists and ukuleleists can pull that off, but most like a standard like us, they can't. So you set this in place, you get a particular note. Now the velocity is set. Okay, the restoring, and the same thing is true of this. If I check the velocity of this guy, we checked it 100 times, we're gonna find it's the exact same over and over because the frequency is set. Now, for like I said, woodwind instruments or like right now, so the restoring force in this is just tension. The restoring force in air is a little bit harder to say what it is because it's those air molecules. It's kind of what we were talking about earlier. It's the traveling of air into the next air and how far they're spaced out. For the most part, they're traveling at the same speed, so we can pretty much assume that it's a constant route, which is why we can say the speed of sound is 343 meters per second. Again, higher on a hotter day, slower on a colder day because they're not moving nearly as quick in that particular case. But yes, the speed is set by the medium. If the medium is set and velocity is set, and therefore you can control wavelength and frequency vice versa of each other. Other questions? These are great questions. You guys are doing awesome. Appreciate it. Yes, Jake.
In the areas where it's less compressed, do you still hear that?
Yeah, okay, so your brain, okay, when we talk, I think I said this the other day, I wish I knew, I think this is middle C actually. I know it's C anyway. So these are all C. And C's, again, I wish, so much I want to get into it, I apologize. A C vibrates up and down at 256 times per second. Middle C vibrates up and down 256 times per second. The next C up the scale, double that, 512. The next C up the scale does 10 times 1048. Excuse me. You can't comprehend that. Your brain has a reaction time of 0.15 seconds. That thing repeats itself in 1 second 256 times, which means in the amount of time that it would take you to even understand what's going on, that thing's vibrated up and down 40 times. Okay? Your brain can't tell you a rare fraction, it can't tell you a compression. It had to come up with some other methodology of giving you frequency because it can't individually comprehend what's going on. Like none of you are gonna, I'm not gonna play middle C, and you're not gonna go, 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, it was 256 times a second, I can definitely tell. Absolutely. So, no, I'm sorry, that was 257, it's a little bit sharp. No, nobody's gonna be able to do that, your brain's not capable. So our brain, for whatever means, developed this ability to take that vibration, take that frequency, and give you a thought. Okay? When that vibration comes in, it makes a particular electrical signal that runs and tells your brain. Your brain then vibrates kind of at that 256 times a second and goes, yeah, we can't tell them 256 times a second. That's going to short circuit the brain. So instead, we'll tell them middle C, pitch. Here's a weird thought. Okay? You've probably heard this phrase in relation to color before. Somebody says, like, how do we know that you're red? It's the stoner conversation. Okay, if you've ever been around stoners, they have the conversation like 20 times every time that it ever happened. But is your red the same as my green? It gets worse. It gets so much worse. All right. So your perception of green and red and purple and pink, even pink, all in your head, completely in your head. So we don't know if your pink and my red and mine and his green and your blue are in fact the exact same color, and we've just been trained otherwise. But it gets so much worse. Sound is also the exact same way. Maybe what I hear is middle C, you hear is G, or you hear is F, or let's get even worse with it. Maybe what I hear as sound, you see as color. And we have just been taught that those things are associated together. What if I look around the room and I see a myriad of colors, and that's what Kieser experiences when someone plays a song? What if his sound, it gets worse, it gets so much freaking worse, all right? Frequency is how your human body experiences the world around you. So, touch is because of a particular frequency of molecules hitting me right here. The feeling of touch, the sound, the hearing of sound, the eyesight. Damn it, it's every single one of your senses is programmed into you by the computer that is right up here. So who knows if they're mixed up, because we can't live inside each other's head. But here's what we do know. There have been case studies with gentlemen or people that have had strokes. And in a stroke, essentially what happens is the brain does not get enough oxygen and breaks. Okay? And there's been a case study in which the brain broke. And essentially, the way I always try to like have this imagination of these ideas is like there's like a library in our head, and somebody comes along and 256 hits, and they tell the librarian, and the librarian says, "Go get that book." Middle C. Tell the middle C. Tell the middle C. Okay. And then 5.25 times 10 to the 14th hertz comes by, and it goes, "Tell them red." Tell them red. That's red. 100%. Okay. So the brain has a stroke, and it's kind of like someone came into the library and pushed over all the books. And the librarian tried to put them back, but there's a lot of books up there. There's a lot of thoughts. And so it's very possible that books get flipped. And this particular person, their entire life, normal, and after the stroke, would hear light and see sound.
What?
And that sounds a little bit strange, but does anybody in here have perfect pitch? Okay. Do you see a color when you hear a particular? Yes. See, people with perfect pitch, the fundamental idea is this thought that, like, while the rest of us kind of have these different scales that are kind of just independent from one another, okay, people with perfect pitch have, like, crossed over scales. And so while a particular note is played where you and I just hear it, they hear it and see it at the exact same time. Arguably, perfect pitch is something of a mutation that is kind of inadvertent, which is not on purpose, but it has amazing benefit, and therefore, don't get me wrong, that's every mutation. That's how it works. Okay, I'm sorry, I'm getting away from stuff, but we got to get one more topic down. All right.
Show how you see it.
So much cool conversation that we could have. I gotta get to this last thought. The last thought is this. The whole culmination of all of these two ideas together is what is known as standing waves. Goodness, I'm trying to talk and say stuff at the same time and I'm writing the right. Standing waves. Okay, standing wave is what you have already seen. It is this. It is a wave that appears to almost not move. Okay? Is this wave not moving? No. What is happening is that there are two intersecting waves going back and forth right now. Why are there two waves interacting with each other? The first wave is caused by my hand going into it. But what is going to happen when my wave hits that boundary over there? It will reflect and invert, creating a reflecting wave coming back the opposite way. If I choose the exact right frequency that corresponds to the exact right wavelength, what will happen is that they will always build, they will always constructively interfere at the same spot, and they will always perfectly destructively interfere at two other spots, making it look like it's not moving even though these are two waves corresponding. So probably the easiest way to see it, here, hold on. I gotta get a higher frequency, gotta get the right frequency. It's right here. The areas of constructive interference are what are known as antinodes. Okay, the two antinodes in this particular one, where you can see the big one over there and the one right here. And the way that I can prove that it's interference is look at how much my hand is going up and down. Hand is going up and down maybe 5-10 centimeters. Is that the amplitude of this in the middle? Which means the only way it could get above 5 to 10 centimeters is if it constructively interferes with another wave. Also, if you look at the very middle of that, despite the fact I am putting a wave into the middle of that right now, it's not going anywhere for the most part. Obviously, we're just looking at bouncing back and forth. That's what's known as a node. A node is an area with complete destructive interference all the time. To help you visualize this a little bit better, I saw a question. I'm going to wait just a second because I want to put this up here real quick. To help you visualize this a little bit better, let's pull this guy up here real quick. Where'd it go? Where'd it go? There it is. Oh, darn. Okay. Open with, paint. There we go. All right, here we go. So it's kind of hard to track here, but let's say the blue, and by the way, this is totally one of those things that you can kind of like flip your brain perception and make it go the other way. So I'm going to say blue is moving to the right. Okay, you can actually 100% make blue move to the left, so humor me, pick a color, I don't care. So we're going to say that blue is what I'm putting in, okay? And what's that? You're not seeing blue?
No, sorry. I was just thinking out loud. I'm not seeing it go to the left.
I'm saying blue is going to the right. And again, this is a mind-bending thing because you can absolutely make it go to the right. You 100% can. All right, let's do this differently. Pick the color that's going to the right in your head. Great. Blue, green, don't care. Okay? Now, here it goes. It goes to the right. The green is going the opposite way, or vice versa, yes? You see that one's going right and one's going left. You see it, green and blue, not black. Don't worry about black yet. Just focus on green and blue. One's going right, one's going left, yes?
Yeah.
Okay, now, if you focus on this area right here, only this area, what you'll notice is that blue and green are always equal and opposite of each other. Always. And if they're always equal and opposite of each other, what happens? Complete destructive interference, which makes it look like they're not moving. Despite the fact they are moving, they're just getting the opposite wave the entire time. Now, if you move a little bit, quarter of a cycle to the right, what you're seeing is that they do kind of like meet in the middle, in which case the line stays straight, but then they stay on the same side. These are the high peaks and what are known as antinodes. The thing that I would want you to see about this in the lab is this is an important thing. This only occurs for very specific frequencies. The easiest way for you to see this, at the end of today, tomorrow, sometime, I'm going to leave this up so that you can do it yourself. The easiest way to see this is to start with what is considered the lowest frequency. Here's the lowest frequency right here. Okay? Now, while it's going, attempt to get to the next frequency. What you'll notice is that this is working perfectly for me, because watch. The frequency I'm putting in is also what's coming back and hitting me in the hand. Remember, what's traveling through this energy is going to be a force that goes into my hand, yes? Now, if I try to go in between and go a little faster, my hand starts getting resistance because it's not hitting at the exact right frequency. But the moment I settle into the next one, here it is, you'll notice my hand nicely is being hit at the exact same frequency that I am putting out, creating the next standing wave. Now we can do another standing wave, okay? Just kind of geometry here. And geometry, so I can kind of go a little faster. So I should be able to, instead of getting, I had one antinode, then I had two antinodes, and now I'm going for three. There it is. There's three. There's three. Let's see if I can get four now. It's going to be, the three to four is probably the hardest transition because it's, there it is. I got it. 1, 2, 3, 4. And notice as I have like 4 of these packets, okay, and I say packets because they kind of look self-contained, but remember that one of these packets is just really one of the cycles, one of the half of the cycles, okay? Remember that 2 of the packets is going to give you a full cycle. What's happening is my frequency on the hand is going up to wavelength of this. It's getting smaller. Here, biggest wavelength right here, this is half of the cycle, so it's twice whatever that distance is. Now I go again for the next cycle. My frequency has gone up, and now my wavelength has gotten smaller. That's a standing wave. Do your homework tonight, do your research tonight. We'll talk more tomorrow.
That's not fair. This is like a 3-year class.
That was my voice.
I'm gonna